Router ID is like the ID card of the device. Then the generated LSA will be associated with the router ID. So they cannot easily conflict. Router ID has a strict configuration format. It is an IP address configuration format, aka dotted decimal. It has nothing to do with IP address. It does not require a suffix mask. This is just a configuration format. How do we usually configure it when we do experiments? Typically, on each device, we up a loopback port. Up a loopback port on R1. In R2 this also up a loopback port. There is already a loopback port on R3. Is 3.3.3.3. R1 here is 1.1.1.1. R2 here is 2.2.2.2. Then I use the address of the loopback port as the router ID of the current device. When we experimented, R1 router ID is 1.1.1.1. R2 router ID is 2.2.2.2. R3 router ID is 3.3.3.3. It is convenient for you to do experiments. We usually have to configure the management address for the device in the project. We have to configure the loopback port address for the device. If it is configured with 192.168.255.1 24-bit mask, then R2 is 192.168.255.2. R3 is 192.168.255.3. There may be many devices in a network segment. Just run OSPF. We usually configure it the same as the loopback address. But we are on the project. It is usually not written as 1.1.1.1. Sometimes we plan based on the overall address. Still tend to write like this. That is, there is a dedicated network segment like this. Use these devices as loopback addresses and router IDs. This is a simple configuration principle of it. Now its configuration format is dotted decimal. But it's not an IP address. For router ID, it can be generated in two ways. Take a break for a while. The first is called artificial configuration. You can manually configure the router ID. We usually recommend this way, because you can manage it yourself. It doesn't matter if you don't configure. It can be automatically generated inside Cisco. If there is a loopback port, then select the one with the largest IP address as the router ID. If there is no loopback port, then select the router ID with the largest IP address of the physical interface. For example, now R3 has a loopback port on this device. Is 3.3.3.3. Now this has an interface address. Is 23.1.1.3. Suppose R3 is connected to R4. Then this interface is 34.1.1.3. Then if there is a loopback port on this device, if you have not configured router ID, then the device will use it as its own router ID. If there is no loopback port on the device, then the device will regard 34.1.1.3 as the router ID. The IP address with the largest physical interface will be selected. It's a rule in Cisco. And the router ID has a feature. As soon as it is determined, unless the device is reset, or OSPF process reset, otherwise it won't change. Now for router ID. OSPF is running between devices. The device is sending out LSAs. The device is receiving and synchronously maintaining its own routing table. Router ID cannot be easily modified. You can reset OSPF. Changed after reset. Okay. Let's go on. There are other key parameters. We'll also have a concept of regions. I just mentioned it to you. Have an area code. First of all you need to know OSPF itself is multi-area oriented, because it is aimed at medium and large network environments. So its overall support and scalability are very strong. It can support a lot of devices. Then when the number of devices reaches a certain number, we'll find out all devices in OSPF to exchange LSA with each other. Synchronize the overall LSDB. Now the LSDB in the 3 devices is this big. If targeting a single area within a range, we want it to have 50 devices, even 100 devices, 200 devices. If the OSPF protocol is running, the equipment is in a large environment. To sync this bucket, then the bucket will become extra large. That is, in the whole database. It even needs to hold the LSA of hundreds of devices. Relatively speaking, its overall load will be relatively large. Equipment will be more difficult to handle, because the device has to calculate. It goes to any other core node in the entire network path. For example, now the data is going to this device. It is equivalent to a node in the network. This device is meant to perform calculations. If the number of devices is very large, the path calculated by each device will be very long and very complex. For equipment, it will have a higher load. Actually, there is no need for this. We're going to divide the area. For example, in the future you will find in the project, we are going to run OSPF. Then a certain piece of your business is placed in one area. Usually it's the core business. Will be placed in this position. There will be some other areas next to this area. This is the division rule. There is a zone 0 here. This is called the backbone area. This is an area that OSPF must have. Then the other zones can be zone 1, zone 2, and zone 3. All areas must be connected to the backbone area. There will be a device in the middle. This device is called ABR. It is a router at the border of the area. We only learn a single area in the NA stage. But everyone must first understand the concept of multi-region. The red circle I drew inside this area are some internal devices. Devices inside the region will only synchronize LSDB within one region. For example, between these devices, including this interface also, they go to synchronize an LSDB. Then, for region 3, these are the devices. Their interface. They go to sync LSDB. So about how the final regions interact with each other, you will learn in NP. At this stage, you only need to know that OSPF is multi-area. So, when we configure, must also specify the region. And for regions, let's go back to this picture and say, if you want to establish a relationship between R1 and R2, then the two interfaces must be in the same area, must be in the same region. This is a prerequisite for their data to be synchronized. If you take the IE test in the future, there will also be corresponding questions. Neighborhood cannot be established. The reason may be that the area code is inconsistent. OSPF is based on interface division. Assume this interface belongs to area 0. This interface also belongs to area 0. But the left interface of R1 can belong to area 1. It's okay. Because the division of OSPF areas is based on interfaces. We often don't say where the device R1 belongs to. Rather, it means that an interface on R1 belongs to a certain area. These two devices you want to establish a relationship with. Their interconnection interfaces must be in the same zone. So the area code must be the same. For the entire NA stage. All the configuration we have done now, they were all done in the same area. Let's get acquainted with the basic configuration. So this is what we call the conditions. For establishing a neighbor relationship. For OSPF. This area code is also called area. It has a rule. Area code if the same. Then the same region. If the area code is different. Different regions. LSA has a synchronization. A prerequisite for synchronization is must be in the same region. LSDB will not be synchronized if different regions. And we are currently learning. We will study the backbone area. The backbone area is area 0. Then there are non-backbone areas. That is, any area other than area 0. You can also define your own. A non-backbone area is a non-area 0. This is the third parameter. Area code. Down to the last one. It cannot be said to be a parameter. It can only be said to be an action. For OSPF. Let's build a neighbor relationship. It is necessary to use the interface. In fact, EIGRP is the same. They are all through the interface. So how to put the interface in OSPF? This is also called network. We will also configure it today. There are two ways to build a relationship. One method is called the declaration under the region, or called under the process of declaration. Its overall configuration format is the same as EIGRP. Declare a directly connected network segment between the two, followed by a wildcard mask. At this stage, we can understand it according to the anti-mask. Or, we enable OSPF under one interface. It is also equivalent to declaring it. These are two different ways. In fact, there are no more parameters. We will start to look at several states next. Just now there are messages and statuses in the PPT. Let's take a look at this state first. In addition to the 5 types of messages we just mentioned, the state is also something we have to learn. For equipment, there are 8 states. Among them, we will not discuss this attempt now, because it's almost unheard of now. There is no application scenario for it. So we call OSPF 7 states. By default this will not be mentioned. OSPF was created earlier. It supports many ancient network types. Well, like this NBMA and frame relay. This environment is no longer seen. In fact, there are very few point-to-point operating OSPF. Early OSPF was applicable to multiple link types. It can support. Then let's look at the remaining states. First look at down, followed by init. Is now called initialization. Then two-way. It is equivalent to a watershed. Further down is xstart. The next one is exchange. Next is loading. The last one is full. Okay. Let's explain them one by one. These are the 7 states. In the process of message exchange, the state will be switched. So how do we switch the state? Let's look at the 5 messages. This part of the message is a bit boring. So please pay attention. Let's talk about the hello packet first. I have told you about the hello message. If I want devices to learn from each other the network segment behind it, first they have to establish a relationship. That is, R1 is now announcing their directly connected network segments. Or declare its interface. Declare into area 0. Then when it is announced now, this interface will send a hello message to the outside world. Then it is in the process of sending the hello message. For example, R2 has not been released yet. R1 is sending out. This process is actually the sending process of the hello message. So now R1 is declared finished. The R2 interface is also open. Declare it too. Let it also start sending hello packets. Then both R1 and R2 have received the hello message from each other. Then an OSPF relationship can be established between them. But for devices, for example, now there are two devices. One on the left, one on the right. There is a line between them. This is device 1. This is device 2. So how does this state switch? First of all, they exchange hello packets. Then please pay attention. At the beginning they are all down. This neighbor state machine means the device sees the status of neighbors on its own device. Like the message we just saw. I don't know if you've noticed. This is the state of the neighbor. This is the state of the interface. This full is. R1 is on this device. C2.2.2.2 the interface between this device and R1 to establish a neighbor. Whether they are neighbors. There is no interaction when the device is just turned on. They do not start running OSPF. They are actually down. For now. Device 1 is running OSPF. Then I configure an address for it here. 1.1.1.1. Device 2 is 1.1.1.2. Now that the device is powered on, device 1 starts sending hello packets to the outside world. Then this hello message will be sent to device 2. As long as the interface declares, device 1 starts sending. This packet is then sent to device 2. Please pay attention. When device 1 first started sending, since device 2 hadn't been announced at the time, so device 1 is sending out to introduce itself. When device 2 is also running, it received this hello packet from its own interface. The content inside is the information that device 1 is describing itself. Then if device 2 receives the, you will learn the structure in the hello packet in the future. The hello data packet will carry the router ID parameter. In details, it can see that there is a device 1 in the current environment, including the information of the interface of device 1. Device 2 sees both. Then now device 2 will switch device 1 to the next state. When it looks at device 1 locally, the device 1 it sees is the second state at this time, called init. So now device 2 is equivalent to receiving. Same. After device 2 is turned on. After running OSPF, the hello data packet should also be sent out. So at about the same time, device 1 will also receive the hello message from device 2. Then it will also set device 2 to the init state at this time. And the following state. When the device receives the message for the first time, everyone must first be clear. For example, device 1 sends only itself. Device 2 only sends messages to itself. Then when a certain moment, device 1 receives the hello packet from device 2. Device 1 is now running OSPF. Suddenly received a hello data packet sent to it by other devices. Tell it the interface address is 1.1.1.2. Router ID is 2.2.2.2. It knows now. A device came into the environment and wants to establish a neighbor with it. So now it will send hello packets again. But this time the hello data packet will carry the router ID of the other party. This is called an active neighbor. That is, when it sends the hello packet again, it will also bring equipment 2 inside. It means that device 2 has now received the hello packet. This hello packet will be sent to device 2 again. Device 2 now received later. It finds that the packet sent by device 1 has its own router ID. Then it knows that device 1 found it. Then it proves that the two of them have established a neighbor relationship. Now we have reached the two-way situation. Then vice versa. Device 2 receives the hello packet sent by device 1. Also recognize device 1. It's in the hello packet sent back. Will also carry the name of device 1 again. So the same. Device 1 receives the hello packet from device 2. It has its own router ID inside. It will also set the opponent to two-way. At this point, the two of them enter the two-way state. Then the difference between init and two-way is. Init is. The device has received the other party's hello packet. But the other party's hello packet does not describe it. But since it received, it thinks it is init. Then at some point, the device received a hello packet. It is described in the packet. That is, the other party knows it. And the other party also thinks it is their neighbor. After receiving, the device will see the other party as two-way. Everyone will find out. In fact, the above three states. The hello message is exchanged at this position. That is, we can use the hello message. Complete the interaction of the first three states. They complete the interaction based on the hello message. So the hello message establishes a neighbor relationship. Eventually until the establishment of neighbor relations. This is the process between them. But the specific parameters you will learn in NP. There are many parameters. So in the NA stage, let's understand its process first. Don't have too much psychological pressure. That is, two-way state. In fact, a neighbor relationship has been established here. In the OSPF we just talked about. To exchange the corresponding link state information. Then in the state of two-way, there is actually no interactive state information between devices. In fact, there is no expression of any information. It's just two devices saying hello. They do not have any LSA parameters. They did not complete the synchronization of data. So let's look down. The next state is called xstart. First of all you need to know the part below these states. It's all about the database. That is, these are the interactions with the database. About xstart status. You will learn in NP. There will be a master-slave relationship election. So what does the master-slave relationship mean? I will give you an example. We're going to sync this thing now. Called LSDB. Then before each device exchanges information. Then the device itself will have a lot of information. There are many LSA. Then here. In fact, they have their own generated LSA. Locally has its own LSDB. That is, the device originally has its own LSDB. Eventually all devices are synchronized into the same. Then when the device is syncing, the device will not send all the information to the other party at one time. You have to think about a problem. Let's say this is R1. This is R2. There is a segment here. If it may have done some other operation on the device. As a result, information devices on some network segments have. Like you order in a restaurant. This is you. This is the man from the restaurant. Suppose you have eaten 12,345 of these dishes. There are 124,789 of these dishes in the restaurant. You want to eat something you haven't eaten. The network segment is the same. Has some content for all devices. It doesn't want. Then when you order, you need to look at the menu first. There are 124,789 of these dishes in the menu. What do you want to eat? You need to order first. Then the chef cooks for you. Instead of directly making a portion of every dish for you. This is unreasonable. Duplicate information for the device. Is useless. The device also does not want to receive and process. So, facing the future. The whole environment is bigger. More equipment. The more network segments per device. When the device requests, do not send repeated information. So when OSPF is synchronizing, They don't send all the information at once. So how can I try to ensure that conflicting information is not synchronized? This is the first question we will discuss. Let's think about another question. This involves the master-slave I just mentioned. But for OSPF, devices are now syncing information. It does not provide a confirmation mechanism. It is equivalent to sending this data. The peer may not be able to receive. You may not be able to collect. So if R1 sends data to R2, it thinks that R2 has received this data. But actually it doesn't receive. The resulting databases are different. That is, their LSDB are different. Because R1 sent it to R2 but R2 did not receive it. Then they end up computing the information incorrectly. If you want to ensure that LSDB is completely consistent, it is necessary to ensure that the sent information is received by other devices. So it's actually a question of reliability when syncing. Then the reliability. We do not give a detailed explanation in the NA stage. It is actually a master-slave relationship. That is, when the device is syncing, we will elect a master-slave to determine who initiates the sync first. In the process of syncing, we're going to do an implicit acknowledgement. It will have a serial number inside. We increment the serial number to represent that the device has received the last message. The specifics will be learned in NP. Let's first take a brief look at the process. Now the equivalent of 12345 and 124789 is not a menu. This is a summary of some of the link states the device has. That is, R1 now tells R2 it has such a message on it. But R1 only sends one directory to R2, which is equivalent to it sends the specific destination network segment to R2. But the specific value in it is not published. Like cost, router ID, etc. Information like this is not sent. If R2 has information about R1, then it will not ask for R1. If not, ask R1 for it. See what I don't have now these. What we said. This is the meaning of out-of-sync conflict information. We don't send real root entries directly. Instead send a digest. This is the first question. Out-of-sync conflict information. Because we will send the table of contents and summary. Let's talk about the scene in which this is carried out later. But first I can tell you that in the process of sending the directory and synchronizing the summary, we use DD packets for interaction. You can see it here. It's called database description. You can also understand that this is a summary of the database. Before DD message exchange, it will actually first exchange a set of empty DD packets. We call it empty DD. In the interaction of the first group of messages, there is no summary. It only uses some parameters to elect the master-slave. Then it will be decided who will start sending this summary first. It will carry a serial number inside. Is used for confirmation. But the question of reliability. Too far away for us now. In the process, we use the DD message to exchange information summary. Then when the summary of the information is now complete, we're going to start making requests next. You can see that R1 does not have this 789 locally. It wants to ask. This is the request. For example, now R1 is about to start sending packets. The packet it sends is the LSR packet. So what will be in this message? R1 now wants 789 from R2. Such as a certain moment. The device wants to initiate a request first. Then it requests an LSR packet to R2. It now wants 789 in R2. Then it also sends a digest. For the whole process of interaction now. Actually in the exchange state. In the state of XStart just now. We will go to the election of the master-slave relationship. Then interact with DD messages. Further down is the LSR. R1 starts the request. When this request message is sent to R2, it should reply to R1. R1 now takes these directories to tell R2. Then R2 should tell me the detailed LSA to R1. R2 will now reply. It will reply this information to R1 here. When R1 receives, it needs to send a message to tell R2. It received the message just now. It will send LSAC to R2 at this time. It means that it has received the message sent to it by R2 just now. This process is actually called exchange. The device is in the process of interacting with the whole. Is in this state. Then start the database synchronization. Finally, all the equipment is completed. Of course, this thing is actually R1 local synchronization is complete. It sees the opponent as full. So, how to switch to this state? There are many parameters in it. When you reach the NP stage in the future, just sort it out slowly. Okay. Let's make a summary. The first is the hello packet. The hello packet interacts in the first three states, which is used to establish neighbor relations. From down to init to two-way. The difference is that check if there is a router ID with it inside. If it receives a hello packet with its router ID, it is two-way with the other party. If it is not received with its router ID, is init. Here are the first three messages. The first three states use the hello message. Let's go on. DD packets will be in XStart and exchange state. Carry out the election of master and slave. To represent when the device is syncing. Who initiated. And confirmed during initiation. Confirm each message sent. Then it will complete the master-slave election in the state. They can start to interact with the corresponding directory. They are the DD message interaction directories. Used in a one-time state. After interacting with the directory, they are in loading state. Is about to start making requests. Replying. And finally confirmed. Is requesting information that it does not have. Then the other party replies to it. It sends another confirmation to the other party. This is what we call loading. Then in this state, as long as it's done, it will switch to the full state. That is, it sees the other party as full. For R1, it requests 789. The other party replied to it with 789. It returns confirmation to the other party. Then it ends in the loading state. It will see that the other party becomes full. Why do we often watch the two achieve full at the same time? Because this process takes about the same amount of time. I ask everyone to master the following content in the NA stage. First, grasp the hello packet to establish a neighbor. DD packet interactive directory. These are request, reply and confirmation. You need to know their names and uses. Then I tell you now. When between two devices. When the mutual status of the two interfaces reaches full. Now called adjacency established. This is the key. If between two devices. Only established neighbor relationship. So can they realize the calculation of routing? Okay. Is not possible. Because they are neighbors. No information exchanged at all. So, the neighbor relationship is just a confirmation of the relationship. It means that they are running OSPF on a network segment. Nothing more. They do not have any interaction with the database. So it has no way to calculate the route. And after they finally reach the full state, their adjacencies has achieved database synchronization. As they are now requested, replied and confirmed. Both of them are now 1, 2, 3, 4, 5, 7, 8, 9. After all sync. Route. Make sure they have all the network segments now. So when they reach the full state, in order to continue to use the SPF algorithm to calculate the corresponding route, some students may ask, how do these two relationships work? Let's take a look here. Router ID. Neighbors and adjacencies. Let's take a quick look. For now, the device runs OSPF. They all have to exchange some information. Link state information and routing information must be exchanged before the interaction. Adjacency. Everyone can see. RA says it has 3 neighbors. Remember this? What does it mean to connect 4 devices with one line? I said before. This means that a switch is connected to 4 devices. But we usually don't draw this switch. That means they are on the same network segment. If on the same network segment, they are neighbors. But they are not all contiguous. Depends on network type. We are network types of Ethernet. There are 3 neighbors here. But you can't say it has 3 adjacencies. We can't see what it is now. These parameters are not enough. We can't see now who is adjacent to whom. Just to tell everyone it has 3 neighbors. But not with 3 adjacencies. Let's move on to a question. I will draw a picture. For example, this is a switch. It connects several devices. Connected some routers. This is 4 devices. Haha, a little ugly. Let's say it's 1.1.1.1. This is 1.1.1.2. This is 1.1.1.3. This is 1.1.1.4. Now 4 devices are interacting. Assume that the 4 devices are adjacent to each other. That is, between 2 is full. Let's see what kind of effect will appear. Let's take the device on the far left as an example. For the device on the far left, we have to consider a DD message. DD packet is a unicast packet. I'll just give you an example. For example, all devices are adjacent to each other. The database is synchronized between the 2 devices. So now you have to consider a question. There must be an interaction between the 2. Suppose the leftmost device originally had a 1-2. It has a 1-3. It has a 4-5. It has a 5-7. Interaction between them. Now in the process of interaction, device 1 first interacts with device 2. Then they are synchronized. This becomes 1-2-3. Then interact with device 4 and it becomes 1-2-3-4-5. Then interact with device 3 and it becomes 1-2-3-4-5-7. During this process, device 2 also needs to interact with device 4. It first becomes a 1-3-4-5. Then interact with device 3 to become 1-3-5-7. Then device 4 interacts with device 3. First of all, think about it. If 2 devices interact in pairs, one question you have to think about is, when device 1 interacts with device 4, then device may first have learned the overall information of device 4 from device 2. This process will be messy. The overall process is iterative. That is, concurrent traffic at the same time. Devices are learning from each other. Then you will find, it's like, you go to a restaurant to order food. Everyone's food taste is different. But this is a cook. You both told the cook at the same time. The dishes you want to eat may be repeated. It has no order. And overall it's going to be complicated. It is specifically complicated in. If now R1 and R2 want to establish a relationship, how many times do you want to exchange messages? It sends 5 messages. Respectively. Hello. DD. LSR. LSU. LSAC. Both of them can be synchronized. R1 and R4 exchange 5 kinds of messages. R1 and R3 exchange 5 kinds of messages. R2 and R4. R2 and R3. R4 and R3. There are 5 interactive messages. Then there are 6 adjacencies in total. We call this relationship the full internet. This method is actually very unoptimized. You will learn a lot of scenarios in the future. Neither is fully connected. A total of 6. Respectively. R1 and R2. R1 and R3. R1 and R4. R2 and R3. R2 and R4. R3 and R4. Adjacency. Then you will find, when they establish an adjacency, a lot of information itself is synchronized. There are a lot of interactive messages. But there is no priority. And less valuable. So that's just 4 devices. What if there are 20 devices now? 20 devices still need to establish a relationship one by one. So the whole environment, amount of information synced between devices, will be huge. The number of interactions will increase. In this case you will find, under the same broadcast domain, if the number of routers is more, then the more adjacencies relationships are established. If more adjacencies, then the more messages exchanged. Then there are 2 problems. The first question is, it will consume too much link bandwidth. There is no way to run other data on the entire link. Just run this OSPF packet. The second question is, this affects the processing performance of the device. Now the device has been receiving messages. But many of the messages it receives are its own messages. It also costs a portion of the processing power. To see if the content in the received message is useful. That it receives so much. It's useless to find. It will be very troublesome. Here is a formula. Just tell everyone. N times n minus 1 divided by 2. N is the number of devices. For example, now 4 devices. The number of relationships established is 4 times 3 divided by 2 is 6. Let's say there were 20 devices just now. 20 times 19 divided by 2 is 190. You will find 190 pairs of adjacencies. At least 5 kinds of messages need to be exchanged. That's 950 packets. Certainly. When the end device is making a data request, request this list. It may not be finished once. Are interactive with each other. But far more than so many messages. Even thousands of messages. So it is very large. So it will affect the processing performance of the device. When OSPF is in overall development, the developers also thought of this problem. We have a solution. Under the entire broadcast domain, have a DR. It's called designated router. And a BDR. It's called a backup designated router. And there is another character. DR other. It is a non-designated router. Nor backup designated router. Then in this process, let's assume it's a DR. It is a BDR. Then all other devices are DR other by default. Then in this process, what is the difference between it and the 2 relationships we just mentioned? Establish neighbor relationship and establish adjacency. What's the connection? And I tell everyone. DR and BDR are selected in this place among the 7 states. That is, choose before going to Xstart from 2-way. Because the neighbor relationship has just been established at this position. Know each other. The parameters are also almost exchanged. Database synchronization has not started yet. Because of a synchronization, everyone started syncing. So you have to choose before. After choosing, It creates a problem. That is, the entire topology changes. I'll draw it for you. We now elect a DR here. It will establish adjacency with all devices running OSPF in the broadcast domain. This green line represents the adjacency. So why choose a BDR? Because we're going to pick a backup. If one day DR is gone, we're going to let BDR take over from DR. You want a question? Since DR is now a core node in the environment, it establishes adjacency with all devices. Explain that this device is important. Often important equipment. It is absolutely not possible to have only one single unit. There is usually a backup. Otherwise it is called single point of failure. We don't allow this. Choose a backup. DR establishes adjacency with all other devices. And the backup also establishes adjacency with all devices adjacent to each other. Then after establishing the relationship, the two DR other are neighbors. They do not need to establish adjacency with each other. For us now. In the future, if DR other has data or updating of information, it is sent directly to the DR. Then when they sync, just not syncing with all devices, it only sends this information to the DR. Send it to other devices uniformly by DR. I will give you a brief introduction. This is not very important to us at this stage. Just know it. When the device finally performs some synchronization of the relationship, how do they go about it? We just mentioned two multicast addresses. OSPF is a multicast update. We used two addresses, 224.0.0.5 respectively, and 224.0.0.6. The reason why there are two multicast addresses, because of the different roles. One is DR. One is BDR. One is DR other. When we run EIGRP, actually only one. We run EIGRP on a 224.0.0.10. All devices go to monitor point 10. But we run OSPF today differently. They will be different roles listening to different channels. All future DR other updates will be sent to point 6. DR and BDR to monitor point 6. Now the yellow line is listening. The green line is sending. DR and BDR to monitor. That is, all information sent by DR other, sent to this multicast channel. DR and BDR go to see the data in this channel. You can imagine this channel as DR other reports to DR. DR other sent an update. DR and BDR received. After receiving, DR will tell this information to other devices. That is R3. Notify this DR other. DR sends the information to the multicast address point 5. I'm not saying send it directly. Then all other routers. Please pay attention. I'm talking about all routers. All other routers will listen to this point 5. That is, now DR sends the data to point 5 here. Then R3 goes to monitor this. 5. Then it has received the update issued by the DR just now. This is just when DR other is doing an update. If DR will issue an update in the future. For example, DR has an extra network segment. 3.3.3.3. It will send the information directly to the point 5. It is not issued 4.6. Because all devices will listen 4.5. Including BDR will also monitor point 5. Then if BDR sends an update, it will be sent first to all DR other via point 5. Then it is sent to DR through point 6. OSPF is like this. Its message interaction is very troublesome. So it doesn't matter if you can't remember this thing at this stage. Anyway, when you reach the NP stage, You still have to remember. Now just to give you a feel. We said earlier that we chose a DR. I chose a BDR. This means that the device will be updated in the future. Just tell DR and BDR. In the future. The DR will tell other devices. The equipment does not need to be sent all the time. Notice. Between them is DR other. There will be no database synchronization between them. All information is managed by DR. Their overall synchronization process now. You will find BDR seems to have no effect in the whole process. Because it is an alternative. If DR is gone, BDR will take over. So it doesn't actually have any real effect. When DR is gone, BDR will become DR. And then throughout the environment, we'll re-elect a BDR. So it's actually an option. And DR and BDR have some principle of election. Let me tell you first. DR and BDR do not allow preemption. Preemption means now there are DR and BDR in the environment. If both devices are functioning properly, is it not due to joining a device? Its parameters are better than these two. It can become DR. It won't. Because as a DR, it must be important. Core nodes in our network. It cannot be easily changed. In order to ensure the overall stability, it is not allowed to change easily. So how are DR and BDR elected? So many parameters. What are the parameters of the election? All parameters are bigger and better. The first is interface priority. I just said. In fact, the declaration of OSPF is based on the interface. So is the interface priority. In fact, the role of the interface is DR or BDR. The default interface priority is 1. Then the range is 1-255. This is one of its rules. The second is the router ID of our device. The bigger the router ID, the better. Here are the two comparison parameters. Bigger is better. We will adjust the configuration later. So for the current network, if you don't want one device to be DR and BDR, do you know why there is such a demand? For example, you are now networking. According to these 4 devices, this device is terrible. You don't want it to be a DR. Because DR must be a device with better performance. You can manually set its priority to 0. That means it abstained from the election. It is absolutely impossible to become DR in the future. That's what I mean. If you want a device to be DR forever, you can change its priority to 255. Then it will always be DR. Then for DR and BDR, its role is to ensure that under a broadcast domain, reduce the flapping of those LSAs. Just reduce some useless flapping. For a device, it doesn't want so many duplicate updates. I saw some students asking, what scenarios are routers connected to switches used for? As a business. For example, now it is layer 2 switching. Layer 3 switching. We may configure VLAN here. Configure gateway. Further up is the exit. I really don't talk much about this kind of network architecture. That is, in actual work. This is not often seen. Actually, I'm telling the truth. At work you will rarely see. So many routers must be configured in the same network segment. You will know later. The most common thing in work is actually this. OSPF is built like this. Point to point to point to point to point. It's all like this. But when we study, usually learn like this. But you will learn NP in the future. I will tell you about the scene. OSPF inner line network. In fact, I see more connections like this. Precisely because of this. We can also manually change its interface to point-to-point. Let it not choose DR and BDR. Save some time. Here are some optimizations you will use in the future. In fact, in the network, point-to-point is the most common way to see. We'll start configuring. What we just talked about are actually some divisions. There's still a little knowledge left. Let's briefly talk about the network types supported by OSPF. OSPF is based on link. This is the interface type, including link type for support. OSPF used by different transmission media. Supported environments are different. Now we are all network cables and fiber optics. The default is the broadcast type. As long as it is a network cable. The transmission medium of optical fiber is a broadcast type. If it is a serial port. WAN technology. This is point-to-point. This NBMA is called non-broadcast multiple access. Just like the old ATM. The frame relay environment is no longer seen. Then there is another one called P2MP below. P2P is called point-to-point. P2MP point-to-multipoint. You will learn something in the IE stage in the future, called DMVPN. But there are not many other application scenarios. Let's make a simple understanding. We are actually talking about it now. But we actually focus on the two of them. The most important thing is that this type. Because the wire network is Ethernet. Okay. Let's go on. DR and BDR. In this environment, select it as DR. Choose it as BDR. The red line represents the current number of adjacency. There are 5 pairs in total. Only 1 pair of neighbors. But you can try it after class. 5 devices. 6 devices. Or 7 devices. Even more devices. You can see. The number of adjacency will be reduced. You can't see it if you look at it this way. Because of less equipment. If there are many devices, you can see the difference. The following is a matter of priority. You want it to be DR. Change it to 255. When we wait for the configuration, we will say, look down. Finally, this is the OSPF area. Let me just say this. I just told you. OSPF backbone area 0. This is area 1. Area 2. Area 3. If on a device. There are some other external routes introduced. Let's not talk about these. Include these ABRs with these names. No need to talk. Because we are only talking about area 0 now. The meaning of this picture is to let you know. OSPF divides the area. Each region maintains a separate database. And 0 is the backbone area. Other regions must be connected to it. Certainly. You will also learn virtual connections in the future. Also called virtual link. You can make it connect manually. Is equivalent to. I make a virtual connection to connect it. But if this way, we'll create a loop. But this thing. In fact, there are not many used in the network. That is, it is absolutely impossible for you to see someone using a virtual connection on the internet. But what we learn, you still have to learn this technique. If you plan, these areas must be separated from area 0. That's a technical problem. Let's make one last point. OSPF overhead. It is called metric in EIGRP. Actually, this is the routing metric. In fact, it can also change the bandwidth in OSPF. It is the bandwidth reference value divided by the bandwidth. Cisco is 8 out of 10. You just know. The greater the bandwidth, the smaller the cost. Therefore, OSPF will choose to take the link with large bandwidth. But what we modify here Does not change bandwidth like EIGRP. We just change the cost directly. Because its parameter is based on the bandwidth. So it's more monotonous. It's not like EIGRP. 5 references in EIGRP. You can't calculate a comprehensive value and change it directly. But OSPF only refers to the bandwidth. So this value based on the bandwidth is also unique. So you just change the cost directly. Okay. All of the above is the theory of OSPF. Next we configure. Let's turn the device on. When the device is turned on, let's talk about the scene of today's experiment. This is also the homework for you today. The experimental requirement is: configure the address first according to the plan. Then run the OSPF protocol. Then process ID and area number. R2 This does not allow the network command. I just told you. In fact, it can be declared under the process. It can also be declared under the interface. After that, we will make the left interface of R2 become the DR forever. Then we thought, priority can be modified. And the last, the routing cost of 2.2.2.2 we learned on R1 is always 20. This is a bit complicated to say. Then let's take a look. I saw a classmate ask, is DR generally placed on the core layer device? Generally for us. Not a core layer device. The core equipment is selected with the highest performance. But in fact, everyone is not so clear about the network architecture. For core equipment, we run OSPF there. In fact, it is not to set up this kind of OSPF scene. It has other uses. Generally speaking, we will run OSPF between the egress and the lower device. Maybe give it a default. That is, its structure will be different from what we talked about today. But we generally choose higher performance. It's okay. You have to understand the various devices. Where is it used? First of all, you have to learn the multi-region. First take a look at how it is designed for the entire network. Let's configure it a bit. The first thing to do is to change the name first. This is R1. R2 also configure it. We come to the device R1. We readdressed. Interface E00. The address is 12.1.1.1. No shutdown. Then we go to loopback 0. It is 1.1.1.1. This is R1. Then R2. Also the 00 interface. The address of the 00 interface is 12.1.1.2. Go to the loopback port and configure an address. 2.2.2.2. This is the loopback port of R2. Okay. Our address is configured. After configuration, ping 12.1.1.2. See if you can connect directly. Is passable. So we now start to configure OSPF. It is very similar to EIGRP. First of all, our routers. Router OSPF. Here is a process ID. By default we wrote OSPF 100 here. When we come in, first configure router ID. The format of router ID is dotted decimal. Then we usually configure it as the address of the loopback port. Router ID 1. 1.1.1. After we finish matching. Further down, we are going to complete the declaration. When we enter the announcement, write process ID to it at the same time. So we're going to start making announcements now. First we declare the direct connection. The purpose of declaring direct connection is to establish a neighbor relationship. Is to establish OSPF relationship. Network 12.1.1.0. It is the same as EIGRP. 0.0.0.255. Excuse me. I forgot to write the area here. Followed by an area 0. This is equivalent to. We declared such a network segment into area 0. Or. Declare the network segment where this interface is located in area 0. It means that this interface will be divided into area 0. This is the first. Article 2 Declaration 1.1.1.1. Then the mask is the same. Wildcard. First understand it as an anti-mask. We're done. After the announcement, I will teach you a simple way to view commands. Show run. Let's look at the configuration now. Then here. There's this vertical bar. Pipe symbol. We won't go into detail about this right now. Remember this set of orders first. Show run vertical bar section OSPF. Just look at the configuration of a module. OSPF configuration on my device. A router ID. 41. That is. The loopback port address. And the last internet segment. It's the first one we're talking about. Let's look down. First. The first interface address is finished. This is also done. Now it's time to do R2. Network is not allowed on R2. Then we can only choose the interface to do. I teach you a simple command. We first go to R2 here. We still have to go into configuration mode. Into the interface. Our previous interface is to enter one by one. Today I will teach you how to enter two interfaces. We have a command called range. For example, now I want to declare the full network segment 1, 2, and 2.2. I want to enter these two interfaces. First advance to this E00. After that I enter this loopback 0. Press enter and I'm in two interfaces. You see it has changed in front. Becomes config if range. It means that I am now entering multiple interfaces at the same time. Separated by commas. So how do we do it? IP OSPF. Process ID 100. Area 0. Okay. We declare done. You can try after class. There are two ways. First enter this interface. Then declare this interface into OSPF 100 area 0. Exit out. Then enter this interface to declare. Exit out. You can also enter two interfaces at the same time. This is called the declare command under the interface. If you feel that you can't remember the order in class, just go back and watch the screen recording. There is not much time in class for everyone to write commands. After the announcement. Let's check now. See if the announcement was successful. Show IP OSPF neighbor. Let's take a look. For now, you see R1 has a neighbor called 2.2.2.2. This is its interface priority 1. The status between them is now full. And R1 looks at R2. Find out that R2 is a BDR. On behalf of R1 is a DR. Let's take a look at R2. Show IP OSPF neighbor. Let's take a look at it to see what R1 looks like. It considers R1 to be the DR. It sees the neighbor R1. Two interfaces can be entered at the same time on the real machine. We will learn VLAN in the future. Everyone should know. Sometimes you are under the layer 2 switch. How to enter all the interfaces? You can directly enter VLAN 1 lane. Not interface VLAN 1. Then you may be under the VLAN if. Go directly to VLAN 1. You have entered all interfaces belonging to VLAN 1. By default, all interfaces belong to VLAN 1. You have entered all interfaces. Can be configured. Here are some differences between the real machine and the emulator. So what do we want to do now? We want the R2 interface to be the DR forever. Let the 00 interface of R2 become the DR forever. We can choose to change its priority. We enter the left interface of R2. Just change it. We've been looking at each other. That is. Show IP OSPF neighbor. Looking at the neighbors. I will teach you a command to see the device itself. Very simple. Show IP OSPF interface brief. I see that I am now on this device. Some summary information of OSPF interfaces. Then now you can see the device's own loopback 0. Here is a cost. Cost is 1. For R2. I won't talk about other parameters now. PID you will learn from NP in the future. Let's modify the interface priority in R2. Be sure to advance to the interface. Interface E00. IP OSPF priority. Let's check. For now, R2 has a priority. The priority is 0-255. We directly enter the largest. 255. Okay. We changed. Let's take a look when we're done. Now for this device. Show IP OSPF interface brief. Now, R2 can see its status here. It's still BDR. Everyone should know. R2 is looking at himself now. Its 00 interface is a BDR. Let's see on R1. We are watching neighbors on R1. It looks at 2.2.2.2. I found out it was a BDR. That is, whether viewed from R1 or R2. It's all a BDR. This means that our modification failed. For DR and BDR. It has no preemption mechanism. The environment is now selected. R1 is a DR. R2 is a BDR. Then R2 even if the priority is changed to a higher. It also has no way to take away DR. So now you can only choose to reset the process. The reset command is clear. Clear IP OSPF process. We reset now. No more. Press enter. Type yes here. We need to reset. If we reset. Reset on DR device. After the reset is complete, the election will be rerun. Well, let's look at it after resetting here. Show IP OSPF neighbor. It's now DR. Unless it produces an accident. Or you restart the process with. Or restart the device. Then compare the data again. It will be re-elected. So you must at least ensure that the OSPF process is reset. Or you just reset the device. R1 now goes to see each other 2.2.2.2. It's a DR. So let's look at R2 itself on R2. Okay. R2 is now DR. It was just BDR. Now it's DR. Last one left. The root entry cost value of 2.2.2.2 learned on R1 is 20. Let's take a look at R1 first. That is. Now it means that the address of the loopback port of R2 learned by R1. Let's see what the current cost of this root is. Show IP root. About such a root of 2.2.2.2. Here's a 110 bar 11. What follows is overhead. Administrative distance. Consistent inside and out. I also said there will be problems with these two values and doing distribution in the future. But let's leave that alone for now. So how to calculate this cost value? It calculates the inbound direction of root convergence. It has an alias called the outgoing direction of the data packet. Usually we say the previous statement. Inbound direction of route convergence. Let's go back here and take a look. For this device, if R1 can learn the root of 2.2.2.2 in this way. In fact, we have talked about EIGRP. First R2 this loopback 0 to get into the device. Then through the 0, 0 interface of this device, enter the device R1. So actually, we call the inbound direction of route convergence. Through which interfaces is this route transmitted to R1? It's called convergence. So we actually calculate the incoming direction. These two interfaces. A loopback 0 interface. A local 0, 0 interface on R1. Or called the outgoing direction of the data packet. In the future, R1 will send data to 2.2.2.2. Then this data packet has to be sent out from its 0, 0 interface, arriving at R2 this device. Then R2 has to come out from the local loopback port. Find 2.2.2.2. But we often still count in the direction we usually remember. So now there are two interfaces to reach the other party's address. For now, first of all, we must modify its value. We also said to directly change the cost. Just like today we change EIGRP bandwidth and delay. Let's look at the interface bandwidth and delay. Now I want to change the cost of the interface. Let's see what its cost value is. First we are here at R1. Show IP OSPF interface brief. This is for R1. The cost value of the 00 interface of R1 is 10. Next look at R2. Show IP OSPF interface brief. The lookback 0 interface of R2 is 1. 1 is 1. 1 is 10. So here is 11. It is the sum of them. Now we want to change its sum to 20. We have two modifications. Now on the left this is 10. Right this is 1. Then if we only change 1. Or change it to 9. Or change it to 19. We use these two modifications. Then please. Which do you think is easier to change? Okay. It must be more convenient to change the loop back to the port. I will give you an example. If now for the entire route, you have modified the physical interface, then it creates a problem. For example, if there are some other network segments behind R2, assuming it is connected to other loopback ports, there is also 3.3.3.3. So if you modify its routing, modify its cost value. That means, if there are other network segments connected in the future, as long as the final route passes through this interface, all will be affected by its cost. That for the network. We often have a principle. In the case of fulfilling your needs, try not to affect more devices in the network, and some more routing. That is, the impact on the network is minimized. If you are now modifying 2.2, it is 10. R2 now changes itself to 10 as well. Then it will only affect this one route. Then when connecting other devices here in the future, this interface is still 10. It guarantees a unified interface with other devices globally. So we usually modify when we will modify the loopback port. In fact, you will know later in the future. In fact, the cost we are talking about, not as easy to modify as you think. Especially the larger the network interface. We often don't change the cost for it. Generally speaking, we don't modify it like this. If it affects routing, in more cases, we will make targeted modifications. In general, the cost should not be modified easily, because it affects more things. It's not like this topology diagram, just two devices. Okay. Let's fix it. That is, now add the two numbers to get 20. The method I choose is to change the loopback 0 to 10. Modify here in R2. First enter the interface. Interface loopback 0. IP OSPF cost. We change to 10. Press enter. We're actually done changing it now. This is very simple. Let's enter IP OSPF interface brief. Let's check. You can see it now. For loopback 0. Now the cost becomes 10. It was just 1. Then let's go to R1 to look at the routing table. Show IP route. It's 20 here. Then we have now successfully modified. Okay. Let's talk about the last question. This is your homework today. If you didn't understand it in class, you can take a targeted look at the screen recording. Organize your notes by the way. We just said DR and BDR. What is their election principle? First look at interface priority. Second look at the router ID of the device. Then before we modify. That is, before we change the interface priority. We also saw that R2 became a BDR. Because we made R2 the DR. So we changed its priority. But why was it a BDR before we changed it? You can see that the interface priority is 1 by default. Then R2 is 1. R1 is also 1. Then they are better than router ID. The router ID of R2 is obviously 2. 2.2.2. The router ID of R1 is 1.1.1.1. R2 is larger than R1. Bigger is better. Why is R2 a BDR? 1 throughout the broadcast network. Not necessarily the device with the highest priority. It must be a DR. This is the first thing to know. You want to see something. Access time. Access time is the time when the device starts sending hello packets to the outside world. For the device R1. R1 should have been running for a long time after declaring the interface. We just declared R2 to its interface. Then in the meantime, R1 has been sending out hello packets. Then it sends this process. It will have an election time. It is a time to elect DR and BDR. We call this time waiting time. This time is 40 seconds. DR will be selected within 40 seconds. Then if this interface is now enabled, it then sends out the hello packet. After sending it for 40 seconds, there is no device to reply to it. Because they reply hello packets. Compare their parameters and select a router ID. 40 seconds and no one cares about it. It proves that there is no other equipment in this environment. Then it is DR. So now R2 comes back. Even if the router ID of R2 is larger. But now there is already DR in the environment. Once there is a DR, no device can preempt. Unless the process is reset. Otherwise it is the DR in the environment. But when we usually configure, because the configuration is faster. So it usually doesn't happen. Because I will give you a lecture while configuring. Slower. So there will be a situation like this. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMo Education. I'm Grolin Annesley from ThinkMo. I hope today's content is helpful to you. See you next class. Bye classmates.